examples for understanding the relationship between graphs of functions and their derivatives and their second derivatives. So here what I want to give you is a picture of a derivative, and then in number 9, the second derivative. And you want to keep that in mind. This is not a picture of the function, this is a picture of its derivative. So we're supposed to pick out the things that we have been getting from the function by looking at the derivative. So first question is, what are the critical values of f? So remember, a critical value is when f prime is 0 or f prime does not exist. So looking at this graph, if this is f prime equals 0 means the y value of this graph is 0. So that happens at 1 and at 3 and at 5. It doesn't appear that this derivative is ever undefined, so it's just those that I'm looking for. So the critical values are at x equals 1, 3, and 5. Okay, so again, you want to think about this. The critical values of the function is where we go looking for the maxes and mins, but those happen at the zeros, or the x-intercepts of the derivatives. Okay, so when is f increasing and when is it decreasing? Again, remembering this is not f, this is f prime. So f prime, let's see, let me actually go back here. F is increasing if f prime is positive and decreasing if f prime is negative. So generally I find that people can tell me these things, but they don't always put it together when they have a graph. So what I'm saying is that if the y value of f prime is positive, then the function f is increasing. And if the y value of f prime is negative, so the positive happens here. So this is f prime positive, negative, and negative. So it looks like f is increasing. Let's just pretend the graph dead ends at this point and at this point. I love these graphs and I snagged them from somebody, but I don't like that they don't give us arrows or closed circles or open circles to tell us whether it ends. So we're going to pretend it ends. So we're going to say it's increasing from 0 to 1 and decreasing from 1 to 3 and then from 3 to 5. And it is really deliberate that I'm putting these open circles on it. At the end point, it's just dead ending, so it's would be increasing away from there, but right at that point is sort of mysterious. And then at all of these points, the function has a flat spot, so it's not increasing or decreasing. Okay, so now we want to decide if f has a local maximum and where, and then local minimum and where. So we've said our function increases, has a flat spot, decreases, has a flat spot, decreases, has a flat spot. So switching from increasing to decreasing is the one that's going to give us something interesting. So I'm picturing right now a function that increases, has a flat spot, decreases. That's a local maximum. I keep saying it backwards. So it does have a local maximum when x equals 1. To get a minimum, I'd have to see decreasing to increasing, and I don't get that here, so I'm going to say no minimum. Okay, and then last thing, looking at f prime, can we figure out when the function is concave up or concave down? So concave up means the second derivative is positive, concave down means the second derivative is negative. So this one I think is often the trickiest for people. If I'm looking at f prime and I'm asking about f double prime, so from f prime to f double prime tells us the slopes. And then if we were going from f to f prime tells us the slopes of f. So there's this, if it's one derivative down, it's telling you about the slope. If it's two derivatives down, it's telling you about the concavity. So what I want to look at here are the slopes of f prime. The slopes of f prime tell me about the y values of f double prime. So here is all negative slope. So this is f double prime is negative. Here is positive. So from here to here, f double prime is positive. And then slopes are negative. And then slopes are positive. Okay, so negative, positive, it switches back and forth. So concave up is, let's upstairs a little because that's messy. Okay, it's from 2 to 3. So f prime is increasing, f double prime will be positive. So concave up from 2 to 3, and then again from 4 to 5. And then concave down is from 0 to 2, and then again from 3 to 4. Okay, last one. Does it have any inflection points? Absolutely. It has more than one. We switched from concave down to up to down to up. So right here at, what is that, x equals 2? Yes, x equals 2. And then again at x equals 3. And then again at x equals 4. So notice, inflection points, we said this before, but let's say it again. The inflection points of a function are where it's changing bend. So if you're looking at f, its inflection points show up as the bend changing. If you're looking at f prime and trying to find an inflection point of f, it's at the maxes and mins. It's where the slope changes. So all the maxes and mins of f prime are telling you about the inflection points of f. And if you're looking at the second derivative, it's the zeros that you're looking for. It's a little pickier than that, but that's where you go looking for inflection points. Okay, so there's gleaning information from f prime. So you can tell a lot from f prime because it's only one step from f or f double prime. You just have to be careful about which direction tells you what. It can get confusing for sure. Mental gymnastics, but this is really good practice for if you're making sense of all this stuff. Okay, and then for number 9, this is a graph of the second derivative of f, and so we can't get as much information about f from f double prime, but we can definitely get some. So if you're looking at f double prime, and you want to know when f is concave up, that's saying when is f double prime positive, and concave down is saying when is f double prime negative. So looking at f double prime, we're talking about its y values. This is the y value is positive, the y value is negative. Okay, so f double prime positive is from here to here, and negative is on the ends. And we'll just pretend again that this thing straight up ends, since I don't have arrows or anything to tell me. So the concave up, let's estimate, let's say that's about 1.4 to 4.78, 4.8 I'm going to say. And then the concave down is from 0 to our 1.4, and then from 4.8 to 5. One thing to pay attention to is it's fine to do a little estimation here, but make sure you're consistent. If you say this is at 1.4 and then you say this is at 1.3, that's not so good. If you decided that the sign changes at 1.4, be consistent. Okay, and then the question is, does f have any inflection points? If so, where? So this is kind of what I was just saying in the last one. If you're looking for an inflection point on the graph of f, it's where the bend changes. And then the inflection points of f show up as maxes and mins on the derivative. And then they show up as zeros on the second derivative. You do have to be careful because if your graph did this, if this was your f double prime, then you didn't actually get an inflection point. It's saying the function was concave up, and then it straightened out, and then it went back to concave up. So you do have to get the switch, but we don't have anything weird like that happening here. So the where is at those two, and we'll say approximately, those two values we picked out before. It switches from concave down to up, and